Hey everyone, today we're talking about vector-valued functions, and vector-valued function we'll define on the next screen, but the main focus will be to be able to find velocity, acceleration, and the direction of motion, as well as a couple other things related to vector-valued functions. Okay, so vector-valued functions, we have a couple things that we want to know about them. So if you have a function that is defined as f of x equals f of t and y equals g of t, so the two pieces together, t is some time interval, then the point x comma y can be defined as the point f of t comma of g of t. And this set of points makes up the curve in the plane that is the path. Then you can write this as a vector. So you can write it as r, which is the same as writing it in the form of a vector OP, or whatever you want to call it. Can be written in component form. So f of t, g of t is the component form, or an I and j form, f of t, I plus g of t, j. This thing here is called the position vector from the origin to the particle's position t. F and t are called the component functions, which then makes r the vector-valued function of t. So it's going to basically have a function in the f spot and a function in the g spot, and that's what makes it this vector-valued function. Okay, up here we have the definition of the derivative of a vector-valued function, and I could take a long time to go over what all of this says here, but I hope that you recognize the limit definition of the derivative when you see it. But you could do a whole bunch of work, and the limit definition of the derivative of this vector-valued function will just turn out to be df dt I plus dg dt j. So the derivative of the f portion, or the I component, and the derivative of the g is how you get the derivative at a point. Then we have a whole bunch of different rules down here. I'm going to talk through them a little bit, but feel free to pause, copy down the rules onto your paper, and then fast forward through my voice if you just want to copy down the information. So we have velocity, which of course, as you know, is the derivative of the position function. In our case, the position is r, so dr dt will be the velocity. And then we have speed, which it looks like it means absolute value here, but actually for this, we're talking about the magnitude of the velocity function, so not absolute value. Then we know that acceleration, just like before, is the derivative of velocity, which would be the second derivative of position, so the second derivative of r. And then the direction of motion is when you take the velocity and you divide the velocity vector, so let's think about the velocity vector, and divide by the magnitude of it. So divide by speed. And then you have something that's called the velocity vector, and this always seems a little confusing to people at first, but it's really not bad. So let me get the highlighter here. You have this thing that looks like the magnitude of v times the velocity vector divided by the magnitude of v again. So it looks like these things should cancel, but really what this is that speed times the direction of motion, okay? So this over here is speed, and then the direction of motion is this part right here. And you should notice that these two magnitudes are not necessarily the same in the problem. They could be two different values, and we'll see one like that. And then this one, the angle between two vectors, should look familiar to you. We did learn this last year in pre-calc. It's the dot product of the two vectors divided by the the product of their magnitudes. All right, so let's do our first problem. So this one says, find the velocity and acceleration vectors, find the velocity, acceleration, and speed and direction of motion at the time pi over 4, and then find, this is the dot product, find the dot product of the velocity times the acceleration and interpret graphically. We won't actually draw a graph for this, but we will explain what it means on the graph. All right, so let's start with part A. I thought I made that the small size, I didn't. All right, here we are. So the velocity vector will be the derivative of the position. So the derivative of 3 cosine is negative 3 sine ti, and then 3 cosine tj. Piece of cake, right? And then the acceleration will be the derivative of that. So the acceleration will be -3 cosine t I plus -3 cosine t j. So that is the answer to part A. Part B then says that we want the velocity, acceleration, speed, and direction of motion at t equals pi over 4. So I have to do some substituting. So v of pi over 4 will be what I get when I substitute pi over 4 into the velocity function. So substituting pi over 4 in there gives me -3 root 2 over 2I plus 3 root 2 over 2j. And then the acceleration at pi over 4 is equal to negative, root 3 over 2, -3 root 2 over 2I minus 3 root 2 over 2j. We also have to find the direction and the speed of motion. Sorry, the speed, excuse me, and the direction of motion. So speed then, remember, is going to be the magnitude of the velocity at this point in time. So we're going to take the magnitude of this, which remember magnitude is the x squared and the y squared, and then of course the square root of that. So this will be, let's see, what do I get here? 9 times 2 over 4, which I guess is going to become 9 halves plus 9 halves, which is then 18 halves, which is 9, and the square root of 9 is equal to 3. Okay, and then the direction of motion is when you take the velocity vector and divide by that speed. So you're going to take this thing and divide by 3. So the direction of motion will be equal to -3 root 2 over 2 divided by 3, I, and then plus 3 root 2 over 2 divided by 3, j. And I hope when you see this, this makes sense because you are going to be able to cancel the 3's in both of these, and you end up with something that would be like a length of 1. So we're shortening it down so that we just know what direction we're going in without having to deal with all of the actual speed at that time. So this is just the direction we're going in. So we're going in the, again, a 45-degree angle, but in the second quadrant. So we're going in the direction of 3 pi over. Part C says find V dot A and interpret graphically. So V dot A will be, remember when you do the dot product, you multiply the i's and you multiply the j's and you add them together. So I have -3 root 2 over 2I plus 3 root 2 over 2j. And I am going to dot that with -3 root 2 over 2I minus 3 root 2 over 2j. And the dot product of this will give me 9 over 2 minus 9 over 2, which clearly equals 0. And so when you have a dot product that is equal to 0, hopefully you remember what that means from last year's pre-calc, but you also could think of it again graphically, which is I'm going to draw a quick little sketch over here. So this vector here is going in this direction, -x, +y, and this vector is going in -x, -y direction, but they have the exact same value, so they're actually the same angle, but kind of in separate directions. Hopefully, as you look at this, you can recognize that this is creating a 90-degree angle. So if the dot product is equal to 0, then the vectors are perpendicular. So if you are able to dot the velocity with the acceleration and get 0, it means you have perpendicular vectors. Okay, moving on. So this example here says, write an equation for the line tangent to the path at the point where t equals -1. That's part A. And then let's just do that and I'll come back and read part B in just a second. Okay, so if I'm going to write an equation for the line tangent lines mean I need to have a derivative so I can find the slope. So the derivative of r is going to be equal to 6t squared minus 6ti plus 3t squared minus 12j. And of course, we are talking about a certain time, so that's what's going to make this a little bit easier to work with. So I am going to substitute -1 in for t and see what the vector is I get. So when I put -1 in for t, I'm going to just tell you the answer. Hopefully you can figure out where I got it from. So I have 12i minus 9j. So that is my vector at time equals -1, and this is the whole entire vector here, right? So, but this also means something in terms of like the length and the direction of the vector. So I could also interpret this as a slope. So remember, this is y and this is x. So I could write this as -9/12. So the slope of the line we're talking about is -9/12, which also then reduces, of course, to -3/4. Okay, so then I also need a point to go along with this. So I'm going to substitute -1 into the original vector valued function to come up with what that vector looks like, excuse me, as a position vector. So when I put -1 in there, I get -5i plus 11j, which I can get a point out of this because remember, this is from the origin to this position. So I can actually use the point -5, 11 to write the equation of my tangent line. So now I'm going to write the tangent line as y minus 11 is equal to -3/4 times x plus 5. Okay, so that's part A. All right, part B. So part B says, find the coordinates of each point on the path where the horizontal component of the velocity is equal to 0. Explain what is happening in the graph of r at this time. Okay, so the horizontal component would be the x component. So I want to make the x component of the velocity equal to 0. So the x component of the velocity is 6t squared minus 6t. Okay, so I'm going to set that equal to 0 and do a little bit of algebra here. And so you get 2 times when this happens. Time equals 0 and time equals 1. Okay, so well, what does this mean, right? So I'm actually going to find some points to go along with this. But what this means is that there is no horizontal movement at this exact moment in time. Okay, so you're not going to have any horizontal movement here. And this might be a good time for you to graph this and take a look at it. If I have time and the video is not too long, maybe I'll show it on Desmos. But you might want to stop the video and graph it yourself. All right, so let's figure out what points we're talking about this happening at. So we're going to go back to the position vector. So at time equals 0, so r of 0, I get a vector out of it. I get the vector 0, 0. But what that really means is at the point 0, 0, I have no horizontal movement. Okay, and then r1 is equal to -1, 11. And this, I'm going to use the point -1, positive 11. And not only does it mean something about the movement of the graph, it also is it's actually giving me a concavity change. This is why I would like to graph it if we have a chance. So this is also causing a change in concavity. And I just remembered that I was overly prepared and actually created the Desmos ahead of time so that I wouldn't make any mistakes as I was trying to type it in. So as we all know that happens to me every so often. All right, so here's how you can actually type this in. So we're going to type it as a set of points. Let me kind of hide some of this so you can not see all of it at one time. So here is my position vector, 2t cubed minus 3t squared, t cubed minus 12t. So this is the x component and the y component. And when you look at these points, can you see how there's this like vertical tangent thing going on here? But also the graph happens to have a change in concavity as well. So something that you'll want to look at in the future or think about in the future. Okay, so part C says, is there any time when the vertical component of the velocity is 0, and if so, where? Explain what is happening in the graph of r of t at this time. So my vertical component is 3t squared minus 12. So I want to figure out if that's equal to 0 anywhere. Looks like this is going to be t squared minus 4. So at t equals, oops, don't care about that, -2 and +2 would be the two places. So then I would find r of 2 and r of -2. So r of 2 gives me the vector 4 comma -16. And r of -2 gives me -28 comma 16. So I want to, all right, so I don't care about these points anymore. So I want it to be the 2 points, 4 comma -16. And point -28 comma +16. So let's zoom out so we can see the points. So here is this one. Kind of looks like maybe you've got some maximum values on here. It's a little bit harder to tell, right? But can you tell that this is most likely a maximum value here? And same thing here, it's a minimum value. So hopefully that makes sense to you, that you're getting a max and min when the vertical component of the velocity is 0. All right, last problem. I've been trying really hard to keep these videos short and they keep getting long no matter what I do. I'm sorry, trying. Okay. So example 3 says that the velocity vector of a particle moving in the plane is given by the function 1 over t plus 1I plus 2tj. We want to find the particle's position as a vector function of time. If r is equal to ln, oh, I just can't believe I just did that. R is equal to the natural log of 2, and this is like the I component part, when t equals 1. Okay, so let's just do part A first, and then we'll move on to part B. So I'm given the derivative. I want to find the function, so I have to find the antiderivative. So I'm going to integrate 1 over t plus 1 I plus 2tj, and this is in terms of t. So this becomes the natural log of the absolute value of t plus 1 I plus t squared j, and then plus c. We have to have a constant. Okay, so now we're going to do some substituting. So I know that this thing is equal to the natural log of 2I when my t value is equal to 1. So I'm going to put 1 in for t. So natural log of 2I plus 1j plus c. Okay, so then these two things cancel out. And so now I end up with c is equal to -1j. So now I rewrite the function that I just found when I integrated, adding that c value in. So r of t is equal to the natural log of the absolute value of t plus 1I plus t squared j minus 1j. And then that's a little bit weird to look at when we're talking about vectors, so we tend to see it factored out. So natural log absolute value of t plus 1I plus t squared minus 1j. So that's usually how you'll see that answer. All right, and then part B says to find the distance the particle travels from time equals 0 to time equals 2. Okay, so the distance the particle travels is arc length. Okay, so my arc length from 0 to 2, I the good news is I actually already have my derivatives because that was given to us in the problem. So this is just going to be the square root of, it's going to be my x component now. So I'm going to use 1 over t plus 1, the whole thing squared. And then my y component, 2t squared dt. And this is absolutely a calculator question. So I'm not even going to spend the time doing any work on this. Is going to be a calculator. And if you don't get the same answer as me, make sure you ask about it in class so that we can figure out what's going on with your calculator. All right, that's it. See you tomorrow.